Gemma may have received the least glamorous upgrades with the biggest real-world impact: cleaner tool calls, better vision behavior, faster attention paths, and an extreme compression idea called TurboQuant. None of these changes automatically creates a smarter model. They target the plumbing that decides whether an open-weight model feels like infrastructure or a very impressive weekend demo. Google officially describes Gemma 4 as an open-weight, multimodal family spanning several sizes, with text and image input, text output, and both pre-trained and instruction-tuned variants. The official model card lists configurations with context windows up to 256K tokens and support for more than 140 languages, although exact capabilities depend on the chosen model. Secondary July 2026 coverage reports fixes involving chat templates, tool calling, vision and OCR behavior, reduced laziness, and newer attention support. Treat those specifics as reported, not universal guarantees. Tool calling sounds simple. Describe a function, let the model choose it, provide arguments, run the function, and return the result. Every arrow hides another failure mode. A missing quote, invented parameter, wrong function name, or explanatory sentence outside the expected structure can break an agent loop before the useful work even begins. The chat template is not decorative formatting. It tells the model where system instructions, user messages, tool definitions, calls, and tool responses belong in the conversation. If training expects one structure while a runtime emits another, even a capable model can produce malformed calls. Fixing alignment can improve reliability without changing model weights. Better formatting still does not guarantee a dependable agent. The model must select the right tool, supply valid arguments, interpret failures, and know when to stop. A serious evaluation needs ambiguous requests, unavailable tools, invalid arguments, multi-step calls, and hostile tool output. One successful weather query proves almost nothing about agent reliability. Reports of reduced laziness likely mean better follow-through on requested tasks, but that behavior also changes with prompting, sampling, context length, runtime templates, and model size. Gemma 4's documented multimodality means images can enter alongside text. That opens practical workflows around screenshots, interfaces, charts, documents, and visual feedback from software agents. Useful OCR requires more than recognizing characters. The model must preserve layout, associate labels with values, follow reading order, and avoid confidently inventing obscured text. Ask a vision model to inspect an error dialog, identify the failing component, extract the exact message, and suggest a next step. Each stage can fail independently. Charts are especially revealing because recognition is insufficient. The model must connect legends, axes, colors, units, and positions before making even a basic numerical comparison. Reported vision improvements deserve testing on your actual screenshots, scans, fonts, resolutions, and languages. A polished demo image rarely represents the messy documents living in production. Attention repeatedly compares token representations while generating output. With long prompts, those operations and their memory traffic become a major part of inference cost and latency. Flash attention techniques reorganize attention computation to reduce expensive memory movement and use hardware more efficiently. They accelerate the operation. They do not rewrite what Gemma learned. A report mentioning Flash Attention 4 does not mean every Gemma runtime instantly benefits. Kernels, hardware, drivers, frameworks, model architecture, and back-end integration must all line up. Kernel speedups should be measured inside the complete workload. Prompt processing, token generation, tool latency, image encoding, and data transfer may dominate different applications. TurboQuant is a Google research family of quantization algorithms for compressing large model vectors and vector search. Its local AI appeal centers on memory pressure, especially around KV caches. During generation, the key value cache stores attention information from previous tokens, so the model does not recompute everything from scratch whenever it predicts the next token. As context grows, that cache grows too. Model architecture, sequence length, batch size, precision, and concurrent requests determine how quickly memory capacity and bandwidth become constraints. Quantization represents numerical values with fewer bits. Done well, it reduces storage and movement while preserving useful behavior. Done aggressively, it can distort the information attention needs. Community discussion summarizes TurboQuant paper claims as pushing KV cache representations below 3 bits with close to zero accuracy loss. That is promising, but it remains a claim requiring implementation and validation. TurboQuant does not add knowledge, improve reasoning, or repair tool selection. It aims to represent and move inference data more efficiently, ideally while retaining nearly the same output quality. If the technique survives real implementations, smaller caches could permit longer contexts, larger batches, more simultaneous sessions, or lower memory hardware. Those benefits trade against one shared budget. A research paper cannot accelerate your laptop by itself. Backends such as llama.cpp need compatible formats, kernels, conversion paths, and maintenance before ordinary users receive any practical benefit. Results can change across GPUs, CPUs, sequence lengths, batch sizes, and models. Measure memory use, prompt speed, generation speed, quality, and stability on the system you operate. These improvements solve different bottlenecks. Templates shape communication, vision expands input, attention kernels accelerate computation, and cache quantization reduces memory pressure. No single layer replaces another. Consider a local coding agent reading a screenshot, identifying an error, calling a repository search tool, and maintaining a long session. Every upgrade touches part of that loop. The same agent can still misread one character, choose the wrong function, exceed available memory, or confidently propose nonsense. Better infrastructure reduces friction, not the need for supervision. Before switching models, verify the exact Gemma variant, official template, image preprocessing, backend version, supported attention kernel, quantization format, and memory required by your target context. Create a small test set from your workload. Record expected tool calls and visual answers, then compare quality, latency, and memory before and after each runtime change. Do not update the model, template, backend, quantization, and prompt simultaneously if you want useful evidence. Change one layer, rerun the tests, and keep the receipts. Google has not magically fixed every weakness in Gemma, but reported workflow fixes, documented multimodality, faster attention paths, and serious compression research point toward a more usable ecosystem. The real breakthrough may be boring reliability, valid calls, grounded pixels, efficient kernels, and manageable memory. That is how an open model stops being a demo and starts becoming infrastructure.